Could this be the most efficient pump ever built? Let us take a moment to consider this new design. First, allow me to show you this smaller version in operation and to describe how it functions. I'm just turning it slow so you can see the components. This is the lower chamber down here, and this is the vertical channel. Spills out of here, and then I just transfer the fluid back down to the lower tank. I built it transparent so you can see the internal channels. Being smaller, it really doesn't show how the inertia works. I have a bigger pump, and once it gets up to speed, it wants to keep spinning. But with this smaller version, you can see the internal components, and also now we're going to pump some fish through here. Okay, now all the fish, look, they're unharmed. Move the fish from the low tank to the high tank. Not one is injured. The actual pump is just this part. This is the low tank, and this is the high tank, and this is my driving mechanism here. So I'm going to show you just the pump now. Take this off. Now this is the pump. This is just the low tank. This is the catch ring where the water spills into and then dumps into the high tank. But the pump itself is one object. There's no moving parts except for the pump itself. What traditionally is a centrifugal pump is a spinning turbine inside of a stationary housing. And in this case, I have this channel, this bow tie shaped channel, and we have an intake, and everything rotates together. So you get centrifugal force moving outward along with these vertical channels. So as your centrifugal force increases, the water will essentially puddle vertically. So you're not deadlifting the water. We're manipulating the force of gravity within this chamber. And since there's no spinning turbines, the fish can pass through this completely unharmed, and they exit these nozzles up here. So I built this small prototype out of this transparent material so you can see all the components of it and how this thing works. You can pump fish or any solids for that matter. It can be stormwater or sewage or stuff for agriculture. Aquaponics works great. The small pump doesn't really show the efficiency qualities, and I have built a larger prototype, a much larger prototype that I'm going to show you now that will demonstrate the efficiency of this pump. Mass in motion. This large drum
and especially the fluid within it contributes to the continual momentum of this design. It acts essentially as a large flywheel.
Want it a little tilted the other way. Okay, right there. There. Yeah, I like that.
A little bit more. Stop.
I'm driving this pump with a handheld cordless drill.
Almost. There we go. That's a lot of water for that little drill.
No, it's just vertical channels, like veins in the bottom, but then these are vertical columns. Right here, these here are hollow. Yeah, and so the water comes up and it puddles on the wall vertically inside. And yeah, so it spins the bucket.
All right. It was moving a lot of water though.
I received a U.S. patent covering 19 points of claim. Pumping fluids is one of the most energy-intensive activities mankind does. Both of these prototypes are built taller than they are wide, which works great for demonstration purposes, but they would be even more efficient if they were wider than they are tall. Imagine building one of these pumps 100 feet wide with a 20-foot intake in the bottom and only lifting the water 10 feet, 15 feet high. Places like New Orleans or Amsterdam or Venice could efficiently remove stormwater in a hurricane or a flood. These pumps act like a floating drum. They're actually buoyant. They can float and just be kept in position with some retaining wheels on the outside. The bigger you build them, the more efficient they will work.